Robbie, can you hear me now?
Yeah, I can hear you now. I thought you weren't talking.
Yeah. Okay, from now on, if you don't hear me talking, say something. Robbie, can you hear me now? Oh,
Yeah, I can hear you now. I thought you weren't talking.
sorry, hold on. Okay, from now on. That's the live stream. Hold on. It's just say something. Robbie, can you hear me now? Okay, here we go. It's gone now. All right. So there's live stream going on. I think I gave you the address for it, but maybe I did.
You did. It was on the Zoom, but it's just on your YouTube.
Yeah, I need to hold on. All right, so I was talking about the tests. So three vocabulary questions. This is next week. I'll talk about it more next week. I'm just killing some time waiting for more people to come. Three vocabulary questions, three read these, three what happened here. Those will be multiple choice. You don't have to write product rule or anything. They'll be choices. Okay. And then there will be three that you have to do, and three more that you have as here's a Desmos link, here's some data, find the average rate of change. I mean, what have we done so far? Limit, average rate of change, derivatives. Okay, so that's three right there, and those are three good ones. So I would expect those as the last three. So now the only thing you have to worry about are the middle three, those three questions where I say do something. They could be anything. That could be the epsilon delta definition. It could be, I don't know, what all those other weird things that we've done. Do we do Newton's method? It could be do a Newton's method.
So that those ones are like basically solved.
Yes. But those are your three regular math questions. Those are the ones which I ask you to use Desmos. So if there's something that requires you draw something, Desmos doesn't draw well. So I'm not going to ask you those questions. But they're quiz questions. You've had them on quizzes. Yes, you've seen question number 4 on the quizzes, like solve this. The other 4 are not. Well, the last one is, but it's a Desmos link. But that's the only one that you have to actually work on. And I don't have any control over what it's going to be. It could be anything. What? The computer picks them, and I'm a little mad at the computer because it picks three. Sometimes it picks two of the same questions. So you did the one question, and then you move on to and you have to do them in order. So you finish one question, and then you go on to the next question, and it's the exact same question, and that's really annoying.
Sometimes I'm thinking it's a trick question. Like, wait, I just did this.
It's just because the way I'm going to try to fix it, but the way Blackboard works is I say pick three of these questions, and it doesn't know. I didn't even know this, but it's not smart enough to not pick the same question. So it picks the same question, and I know this because when I'm grading them, I see the same question twice. I'm like, ugh. And it's not bad if you get it, but if you miss it, then it's two questions you miss. I mean, you could have gotten one of the other questions, then you might have gotten it. But if it's something you're missing and it gives you them twice, then then you get screwed. And I've seen that because that's how I know that I only look at the ones you miss, really. So when I see that you missed the same one twice, I'm like, oh no.
Is paper like completely banned?
Yes, no paper. This is an interview. You show it on the screen. Talk to me about it. If you need to do something, or if you wanted to use paper, you'd say, oh, I would have put this down on the paper, whatever. But honestly,
they just wanted the test to be sort of shortish, right?
it's not necessarily short, but I want it to be entire. When I look at your tests, I want them to be interesting. When you talk to me on the test, that's interesting. When you're sitting with your head down, working on a piece of paper and a calculator, I got nothing to look at. I got nothing. It's just boring to me. I don't know what you're doing. And if I were interviewing you and you put your head down and said, if I said to you, why you want this job? And you went like this, you would not get that job. Okay. They would think you have some social problems. But so I really just want you to, I ask you a question. I want you to answer the question like like I was asked, like your kids were asking you a question, your mom was asking, like, or somebody asked you a question, what is math? I want you to be able to answer it. I just don't, the problem is just I go through this all the time. I don't know I don't know what this course is going to be, how useful it's going to be for you in your world, whatever you're going to do. I hope that it will be useful for you. I try to make it useful. The project stuff that we do, the discussion stuff, that's actually pretty useful. And it can be used in the real world. But like Newton's method, you probably won't see that ever. Epsilon delta ain't happening. I have to cover them, but this is a little politics thing. It says that I have to cover them. And so I do. Doesn't mean I have to put them on tests. Okay. I don't think you're going to use epsilon delta. If you're a math major and you're taking advanced calculus, that's the next time you'll see epsilon delta. That hyperbolic cosine and hyperbolic sine, I have to cover that. But the next time you would use that is 2 math classes later than now. It's actually useful in Calc 3, but it's not useful here. But I have to cover it. So I'm very limited. You'll notice there's like 2 questions I ask about with hyperbolic anything in. So there isn't a whole lot of, I'm just not going to ask you a whole lot of questions I don't think you need to know. But I do put them on the tests and they randomly show. So to give you an idea, the epsilon delta thing, there's a selection of like 12 questions, and the epsilon delta is one of them. So your chance of getting it is 1 out of 12. But it might be you who gets that epsilon delta question. It might be you. Then do the best you can. But honestly, I don't remember seeing anyone miss it. Like when I think back on how many things people miss, I don't remember marking that wrong on hardly anybody. I mean, I don't remember looking at it. So therefore, I think it hardly ever comes up. If it comes up, I may have removed it. It's possible it's gone. Okay. Newton's method, I do ask. That's one. The Newton's method thing, that I do ask because I used to think it was useful. But I don't do anything for me anymore. All right, let me get started. I've got 4 people at home, or 3 people at home, and 4 people here. That's 7 people. We only have 9 people in this class. So, yeah, that's most everybody. Turn my picture off. Okay, so we went over homework 3. That was due last time. The homework 3 is basically quiz 3 and the discussions, which we went over last time. Okay. All right, so the new material, these were all the things that we've done so far. So let me just talk about them for a second. The slope of the tangent, the definition of the slope of the tangent line, this thing, I have to cover that, and I should cover it. And we do use it later on. Like you asked me, what's the derivative of sine and cosine? Well, they use this to find the derivative of sine and cosine. They literally replace the f with cosine. Like this. Like that's what they do to find the derivative of cosine. And then you have to remember that identity, that cosine identity, a plus h is the cosine a, cosine h, minus sine a, sine h. Remember that? I know you don't, but I did cover it in pre-calculus. So that you have to use the trig identity. And somebody did a lot of work to find that they started with the definition and they found that the derivative of cosine is sine. Okay, you can look that up. You can just ask Siri to show you the proof of that, and it'll probably show you just fine. It's been around. It's been around. Here. Come on. What's the derivative of sine? No, it's not saying anything. Here's some information about the differential. Okay.
If you Google it, it does pop up.
Does it?
Yeah. Sure.
Is the derivative of sine cosine? Yes, the derivative of sine is cosine. Told me that. But that's what I'm saying. I don't want you to. Again, this is just me, and I'm sorry for lecturing you like this, but if you were a math major, I would definitely have to cover more of this. But you're not going to see it, and you're not good. They're not going to use it in Calc 2. If you have to take Calc 2, they're not even going to use it in Calc 2. Okay, but that's the definition of the derivative. And when it's done, it's done. Somebody did it, you can just memorize it. You can ask Siri about it. The formula sheet might actually just have it on. Have you seen the formula sheet? Okay, so the formula sheet might be under course info. Let's see. It's somewhere. There's my live stream thing.
Is it under Mach 0? Says we're already.
Probably. No, I don't know where I put it. I know I put it somewhere. Maybe, it might be on my website. But let's see. Should be on the quiz itself. The quiz has a link to Desmos. You'll just see that it has a folder at the top, and all the formulas are in the folder. So that's where it is. Okay. So just save a copy if you want. You can save once it's if it's a Desmos thing, you can save a copy. Yes, you know this.
Yeah.
So let's just take a look at quiz 1. So this is quiz 1. Oh, this one has those extra questions in it. So, okay. Yeah, I should just look at it as teacher and not take the test. Anyway, just a reminder that the test has the same sorts of things here.
However, it's on.
They're all the same. There's more questions on the midterm. There's 20 questions. Here's a link to Desmos formulas. See assorted formulas. Boom. That one right there is Newton's method right there. In case you forgot it. There's the product rule. There's the quotient rule. There's the derivative of a to the x that you'll probably never need. This is derivative of tangent is secant squared. Derivative of the inverses, inverse sine, inverse tangent. These are summations that we use later on. This is the equation of a circle. That's perimeter, area of a circle. Perimeter of a circle, area of a circle. Area equals 1/2 base times height. So these are formulas that go right there is the equation of sort of the definition of derivative. You put the limit in there. This one we use, this is a linear approximation. We'll use that probably next week. This is all that is right there is the quadratic formula, which again, I don't need to know that. It doesn't have derivative of sine or cosine because I want you to know that. Did you see tangent was on, secant squared was on, tangent is on there. I don't think anything shows that if I put on the test the derivative of secant, which is secant tangent, that's the answer. That's what it is.
Right.
It's been done, it's been proven, it's secant tangent. Then someone would have complained to me that my flow wasn't on my formula sheet.
Or like sine squared.
That could be, but that's different. So let's just say if you want the derivative of sine squared, this is definitely on the test. I'm going to make it harder. Okay. And by the way, that was the answer right there. It's that thing. So the derivative of sine squared. So that's the same as derivative of parentheses sine of 2x. Squared like that. You see, it's the same because it's here, same graph, right?
So that would be our answer.
No, you can't answer derivative with the derivative. You have to do, it's a power rule. So you bring the 2 down. Okay. You leave the inside alone. So that's a power rule with the chain rule in it. Then you raise it to the first power, 2 minus 1. See, that's still not right. See, it's not right. That's not right because the graph is fine. Let me just change it to purple. Okay, so I have to take the derivative of the inside, dx of the inside. Okay, hold on. times dx of the inside, which is the sine of 2x. And that should be right. See how the graph is still the same? Okay, still not done because you can't answer derivative with derivative. So let's do this. What's the derivative of the sine? Now we need to know the derivative of sine. What's the derivative of sine? Cosine. See, it's not the same because you have the derivative of sine. Cosine, leave the inside alone and then do what? The derivative of the inside. Now it's the same. No, well, but it will be the same. Okay, you can see how they're all the same. The green is the same as the purple. It's the same as they're all the same. So what's the derivative of 2x? What's the derivative of 2x?
Squared.
No, derivative of 2x. What's the slope of a line? It's 2, that y equals 2x. And what? It's 2. So let's take this out, put in 2. You see nothing changed. So I put 2x there, no. Okay? So it's the same. So I could bring that 2 to the other side, take that 2 and put it with this 2 and make it 4. Okay, and I can get rid of all this other crap. So there's the first power and another parentheses. I don't need any of that. And then it's the same answer, that's done. Okay. The thing about leaving something alone. So I used to go over this, but I'm not going over it anymore. But this was a hard one. Do it this way. That's 6. Secant. There we go. Secant. Okay. Derivative of secant of 2x. What's the derivative of secant? I told you it was secant tangent. Secant tangent. No capitals. Okay, but I said leave the inside alone. So what's the inside? 2x? So where do I put the 2x? In which of these spots do I put the 2x? Because I want to leave it alone. Like with the other one, when I left it alone, I was the derivative of the sine of 2x. I left the inside alone. I left the 2x. I did cosine, and I left the 2x there. Here, because the derivative has 2 things in it, and it only has 2 things in it because of trig identities and stuff, we don't have a single function for secant tangent. But some things we do have a single function for, but we don't. So we have to leave it alone in both places. 2x, and then you have to do times the derivative of 2x. And then you should get the same answer. Just see. So I had a black one, and now it's purple.
Then the answer would just be secant.
Secant 2x tangent 2x times 2. Okay, let's change this to a 2. Okay, I don't cover that anymore because I honestly don't really care. But this was a cute one that I always thought was fun. I was like, ooh, when I say leave it alone, the function might actually have it left alone in a few places. And you might think, oh no, life is horrible. But it's so rare that it comes up. See, no one takes derivative of secant anymore. It's just not a thing. So I don't have to teach this. And so I've sort of removed it. I think it's in the notes and it's in the videos, but it's not something I do anymore. All right. Let me get out of this. Okay, where was I? I was here, agenda. So we did the definition of derivative. In my other class, some people were saying they're just not getting derivative. They just don't understand the concept. And it's too bad because we're going to use, if you don't understand epsilon delta thing, you can move on. If you don't understand this definition of derivative, you can move on. But not knowing what the derivative is going to be a problem. Okay, so I ask in my questions that I ask you, I say, what is a derivative? I say, actually, I don't. I say, give me 4 other ways of describing IRC, which is instantaneous rate of change. And the derivative is 1 over that. So the derivative is not, it's the instantaneous rate of change. It's the slope of the tangent line. It's dy dx. All these things mean the same thing. They're interchangeable. Okay? And that's what these, there's some notation and stuff, but basically it's the slope of the tangent line. So if you're looking for the equation of the tangent line, the equation of the tangent line is going to have the derivative in it, because the derivative is the slope of the tangent line. All this is right here, if you look at the formulas, is just the equation of a line. This is y equals mx, and then there's going to be all the rest of this is plus b. That number, when you take the derivative and multiply it by a and then add f of a, that's going to be the intercept. Okay, but this is a nice way to remember the equation of a line, but we never teach it that way in algebra. But in calculus, it's a good way to remember. Okay, so derivatives. So there are quick and dirty rules for derivatives, and you memorize these. Okay, the first bunch you should know, because it'll slow you down. Like if when I said the derivative of 2x, you should have known that, but that's this one right here. If there's a number, or it's any of this one too, mx, derivative of mx is just m. You just drop the x.
Same if it was just x in there, you would just drop it.
If it was just x, we just have 1. When you drop the x, we get 1. So there's no 1. People don't write 1 all the time. This is the product rule. Okay, this is the quotient rule. These are rules that are used sometimes, on occasion. As I said, let's stop. Oh, okay. They're used sometimes. I'm just telling you that for me, I'm contractually obliged to teach this, and they may be useful. So there they are, but they tend to come up not in the what's going on here rather than do it, because you're going to make a mistake doing these. And if you were really doing it, if it was your job to do this, your work would give you a week to do it, and you would check it twice, and you have the computer do. I mean, it wouldn't. For me to put it on a test and be like, you need to be able to do this, that's not what happened. In real life, that doesn't happen. But being at a conference and having somebody use the product rule and say, I'm taking the derivative here and using the product rule, still not likely to happen, but it might happen. And then in which case you could just say, yeah, I had calculus. I vaguely remember this, but I couldn't do it. But somebody else already did it. And if you want to do it, you can double check it with Siri, whatever. See where I'm going with this? I don't know. I think a lot about why you should. For me, education has changed a lot. Like, I remember why these things were the way they were, and they're not useful anymore. But some people teach math. Like if you took a math class, mostly they won't do it the same way they always did it. And the rest of the department will teach math the way I took math 20, 30, 40 years ago, whatever. They're teaching it the exact same way. And they don't care. They think that because that was the way that they learned it, that's the way you got to learn it. And I'm like, no. Okay. So here's some derivatives. So these are the derivative transcendentals. Again, they're strictly done. They've been done already. So you might as well just memorize the ones I asked you to. E to the x, natural log of x, sine, cosine. Tangent, yeah, sure. But secant, no. Cosecant. I mean, actually, secant and cosecant do come up sometimes, but I don't want you memorizing them.
The log one, though.
The natural log one, surprisingly, yes. The log one, no. The natural log, yes. The log one would be, and you could check it. Again, if you want y equals, let me just do the derivative, d dx of the log, this is log base 10. Actually, no, I'm going to make it base 3. It should graph that, and it does. And the derivative of that is this. If I'm right, I'll get a line that'll sit right on top of it. It'll be 1 over x natural log of 3. So you see how the blue line sits right on top of the red line?
That's-
If I put an absolute value in here, then they're exactly the same. Okay, you see that the reason why the long reason why that is, but the log is only defined over there, but 1 over x is defined everywhere.
That would be right.
If you did 1 over, yeah, that's fine. Okay, we could talk about this, and we will. And we'll talk about it when we get to where am I? I lost it. Oh, that was here.
Yeah.
Okay. Chain rule. This is one you got to know. You have a function inside another function. You have to get used to it. You may not be used to it now because all these little functions that I say, oh, you need to know this, that's great. And they're easy by themselves. Cosine's easy by itself. But when I put a natural log inside a cosine, you have to know I have to take the derivative of the outside function. So it's cosine of natural log. This were cosine of natural log, I would do the derivative of cosine, which would be minus sine. And I'd have to leave the natural log alone. And then I'd have to take the derivative of the natural log. But somewhere in the answers, if you have an inside function, when you're done taking the derivative, that inside function better show up. Like it has to be in the answer. Because like, remember when we did the derivative of 2x, when there was that, where was that? That was, where did we do that? We just had it, yes? I was just playing around with the cosecant stuff. Oh yeah, here it is. There's an inside function. Actually, this is an inside function, sine of 2x. It appears in the answer, sine of 2x. See that? And you see there's a 2x on the inside. That appears in the answer to 2x. They have to, whatever's in the parentheses has to come, in the end, it has to be there.
At these points.
Oh, yeah. Every single time. Because when we do antiderivatives, we're going to be undoing these at the end of this course. We'll be undoing derivatives. And that's how we need that. That's going to be our clue as to what happened. The chain rule does that every time. So here. All right. Chain rule, specifically the one with the chain rule that I thought was important was when you had dx of y to the 4th power. Let's do that. What is ddx of y to the 4th power? Well, it's a power, so you use the power rule. So you bring the 4 down, right? And then you have y raised to the 3rd, but the variables aren't the same. So this is technically, let me just write this down. This is like that. It's a function of x. Let's do it this way. Y is a function of x, like f of x. Okay? So you're leaving the inside function alone. So you're doing the same thing. You're saying, here, I leave this thing alone. Okay? But now, I did the power rule. I left the inside alone, and now what do I have to do? Chain rule says I have to multiply it by what? The derivative of that inside function, which is f of x. Okay? So if I replace those all with y's, that's a y cubed, and that's a dy dx. So, so that's why you see d dx y raised to the 4th is 4y cubed y prime. Okay, the y prime is just the derivative. Okay. Okay, so that's the chain rule, and we do that. We needed to know that last time for what we're going to design. And then velocity and position, it's just the velocity is the derivative of position. Mean value theorem is one of those things. So the mean value theorem is one of those things that comes up sometimes, but it means specifically when the average rate of change is equal to the derivative, the instantaneous rate of change. It's just It's a very specific thing, but it's used for those you're getting a ticket on the turnpike, if you remember that example. Okay. The other theorems I didn't even cover. Squeeze theorem. I don't care about squeeze theorem anymore. It's nice, but since you can use Desmos to find numerical answers of any, so I was watching Mean Girls. I told you this. And then the Mean Girls, they say the limit does not exist. I mean, that's the whole thing. I threw that function into Desmos and graphed it and looked at the graph, and I was like, oh yeah, the limit exists. Like, these people are wrong. Whoever it was who wrote that show wanted to say the limit does not exist. It's artistic license. It was mathematically wrong. But I didn't do any of the squeeze theorem stuff. The squeeze theorem is how to find a limit, and I don't really care anymore. Okay, it was used to find the derivative. This limit right here is a specific one that we use to find the derivative of sine. It shows up in the derivative of sine cosine. But I just don't care. Intermediate value theorem is something we use. That just says that if you have a function that's above the table here and below the table there, and it's continuous, well, at some point it crosses the table. So if you have a positive value and a negative value on a continuous function, like if over here it's positive and over there it's negative, if it was continuous, if I went from positive to negative, I had to cross 0, or I had to cross the table at some point. It's just we use it. It almost makes sense when you see it. We'll use it. I'll mention it again when we get to functions. Not functions, curve. In another week or so, we do curves. So last time we did implicit differentiation. So implicit differentiation is just explicit is when you have something like f of x equals. Implicit is when you have an equation with a y in it. So there's an equation with a y in it. Okay. Hold on. Let me get rid of these guys here. Okay. So remember, this was an ellipse, and those are tangent lines. The red one is the tangent line, is the blue. In order to know the difference, you have to know more than just the x value. You can't just say x equals 3 because this one is x equals 3. Also, you have to say something about the y value. So they'll say something like at the point 3, 3. So when you take the derivative of this, when you take the derivative of both sides, you'll get a y in it, and you'll have an x in it. You'll put the 3 in one, and you put the 3 in the other. Okay. So here it is worked out. The derivative of 2x squared is just 4x. Derivative of 3y squared is 6y dy dx. That's the chain rule, right? So when you take the derivative of this whole side, you're going to get 4x. So the derivative of both sides, sorry about that. The derivative of both sides is going to give you 4x plus 6y times dy dx equals 0. I'm looking for dy dx. So when I solve for dy dx, I can take all this other stuff to the other side, and I get minus 4x over 6y is equal to dy dx. So that's how I solve it. Take the minus 4 and divide by the 6y. Are we good?
Oh, yeah.
Just solve just algebra.
And
then to find the derivative, you just plug in 3, 3. So when you plug in 3, 3, you get 2/3. And that means the slope of these tangent lines are, well, the slope here is minus 2/3. Do you see how it's going down? So it's minus 2/3. If I plugged in 3 minus 3, it would have been positive 2/3. Okay? We go with that. That's an example of implicit differentiation. We are going to use it to find inverses. We're going to use it next week. We're going to use it when we're trying to find the inverses. I'm going to use implicit differentiation, but we don't do a whole lot with non-functions. That is not a function. It's an ellipse. So what is calculus? The study of? No, it's pre-calculus. Pre-calculus is the study. Calculus is the study of change, and what is changing. So this is not a function, but we can still find how it's changing. Okay, that's not a function. So we almost don't care about it. As far as calculus goes, yeah, we can. It's not something we see every day. When was the last time you saw an ellipse? Okay, I'm sure you've seen them all the time, but when was the last time you saw, because a face is an ellipse, by the way. When was the last time you took a derivative of it? Never. Okay, hyperbolic functions, again, these are functions that they're just new functions. The little h's in them, sinh and cosh, they're defined to be this. That's sinh, this is cosh. So there's nothing about them that's sine or cosine. They don't repeat. They have no period. They have no amplitude. They have no phase shift. None of that. They're just, I don't know why they named them. They have identities like trig functions do.
But not part of trig.
They're not part of, but they are part of transcendental functions because transcendental functions are just anything that's a word. Pretty much as like natural log is a transcendental. They're just another type of function that's defined to be the combination. This is this is the average of two transcendental functions, e to the x and e to the minus x. And this is the difference of the two. And that's why they look the way they look. So that one looks like, that's what the hyperbolic sine looks like.
The left side is kind of flipped.
Yeah. It's an odd function, by the way. When we do odd, I don't know if you remember odd and even functions from pre-calculus. It's an odd function like sine. Yippee. Cosine is an even function. This is an even function, just like cosine is an even function. It's symmetric about the axis, but I don't know. I know when we use it in Calc 3. What we use in Calc 3 is the identity, the cosine, hyperbolic cosine squared minus hyperbolic sine squared equals 1. That's what we use in Calc 3. None of the other stuff. We don't use anything else. Nothing. So all this sinh and cosh stuff. I do think that if any of you are interested in astronomy, not astrology, astronomy is the movements of planets and stuff, they might follow hyperbolic functions. And that, so therefore it's useful there. But as far as most people, it isn't very useful. Okay. All right. So are we okay with them? So I just ask all I'm going to ask you to do is find the derivative of hyperbolics. You're going to forget it by the time you get to Calc 3, if you ever get to Calc 3. But the fact that I've covered it, I've done my contractual obligation. And when you get to Calc 3, if I were still teaching Calc 3 and I asked you, you wouldn't remember it because none of my Calc 1 students remembered it anyway. But also none of anyone else's Calc 1 students did either. So that's right.
So that's how it'd be.
That's how it'd be. But one hopes that there's some glimpse of, so it isn't that hard to do in Calc. If you make it to Calc 3, you can remember the identities and stuff. But for here, all I need is the derivative of hyperbolic sine is cosine, derivative of hyperbolic cosine is sine. That's it. Newton's method. So Newton's method was this thing, was a process that used the tangent line. It was Newton's method used to be a big thing back in the day because if you had a TI-83 calculator and you asked it to solve for something, you would give it a left bound and a right bound and a guess. And my students never understood why they needed this. Like, why do I need a left bound and a right bound and a guess? I said, because some programmer wrote a program that starts with that guess and does exactly Newton's method. Create whatever you're trying to solve. It creates a function out of that. Whatever you're trying to solve, it puts it all to one side. In fact, the calculator used to say, set it equal to 0. So whatever you're trying to solve had to be set equal to 0 because that's what Newton's method does. It finds zeros. So if you're trying to find what f of x equals g of x, just bring the g of x to the other side. So it's f of x minus g of x equals 0. You put that in the calculator, and then you would start with a guess, whatever number you want. So you say the number 3. And then behind the scenes, it would go through and do this Newton's method. And sometimes it would come back and say bad guess because your guess was bad. And sometimes it would come back with different answers depending on what your guess was, because that's what Newton's method will do. It depends on the guess. But what we're doing is it's just so much easier to use Desmos and have it do it like calculated, that you don't have to do it step by step the way the calculator does it. But rather you can just create a function z of x equals whatever function you're looking for, whatever you're trying to find the zero of, just say x minus f of x over f prime of x. Here's the function, x cubed minus 6. So I graph that. I see a zero here, minus 2.43. Okay. What I'm going to do, I'm just going to change this function. No. No. Not that. Hold on, I'm going to change that function. Okay. How many zeros do you see? 3. So let's start with the same guess that we have. Minus the other one here, which is minus 1.53. So we'll start with minus 1.53. Minus 1.53. And so that means if you put that into Newton's method, so if you plug in minus 1.53 here, minus 1.53 here, 1.53, you end up with minus 1.53209. Okay, and if you take that answer and plug it into Z again, here, and here, that's the same as doing this. It's the same as doing Z twice. And you'll get this answer. And you see how close they are? And if you do it again, you keep doing it until the answers agree in as many decimal places as you want. So 627, 624. If I do it another time, it should agree that it should still stop. But I can use you see the bunch in the front are not changing anymore. So if I need decimal places, but sure I can do that too. Okay. But that gave me this answer. But if I try one of the other answers, if I try, let's say 1.8, let me just start with 2. So if I start with 2, that's not a particularly great guess, but it does settle down to 1.8 like that. So there's the 1.8 something. If I can do it, I can keep going again until I get it exact. What if I try a different guess that's awful? I don't know. Zero going to give us. Zero gave us this one right here. Okay. What if I use a really big one like 100, like 10? See, 10 isn't done finding an answer yet, so we have to keep going. Z of. So it's around 1.8. Found the 1.81. Okay. But you can have a bad guess because what can happen is since it's this tangent line thing, it finds a tangent line, creates a new guess, and then finds a tangent line, then finds a new guess, and it goes back and forth. It's possible that you could have a bowl where the function goes down, it comes up, and then goes down, it comes up, and just keeps bouncing back and forth and never ends up anywhere. So that's possible. That would be a bad guess. And the programmer would have to do it like 20 or 30 times and then return bad guess. Because this process doesn't take that long. Computer does it like this. If we did it by hand, we'd have to, what we would be doing is x minus, if we're doing it by hand, the old-fashioned way would be x minus, then you take this function, put it on top, and what's the derivative? 3x squared minus 3. That's what this function is. And every time we put a guess in, we have this function do it. It's an iteration of Newton's method. Okay, so if you're going to use Newton's method, you can either do it, you can write the derivative out. Some people do that. But if you're not doing it on decimals, just write it that way. Any of these would be using decimal, it would be using Newton's method.
So when you get those numbers, you plug it in for that.
When you get it, you have to, I just look at the graph of the function and I look for the zero that I'm looking for because that gives me a bunch of decimal places. I already have 153,209. That's a lot of decimal places already.
Yeah.
What is it? 15 minus 1,209, something like that. 153,209. That's a lot of decimal places. And so when I do it once, oh, it can't do it because I did this. Sorry, my bad. I get really close to it already. I'm pretty much done with one attempt of it. If you start with a really good guess, You get to answer right away. Start with a bad guess, you could be sitting there all day.
So you're just looking for a zero?
We're looking for a zero. Look, the zero is because I'm solving this equation equals zero, because I could also be solving this equation. Let me just take this one. I could be solving this. Take the one out, put it over here. That's the same equation. Solving this is the same as what we had before. You're solving that. You're also solving this. Okay? Because, oh, that's not it. It's just having the one on one side or the other doesn't matter. But so as long as you have an equation that you're trying to solve, an equation just means there's an equal sign in it, right? And you say, well, I don't always have it equal to zero, but you always can have it equal to zero because you can take everything from one side and move it to the other side. Okay? All right. Love Newton's method, but I told you one of my problems is Desmos didn't, if you look at my notes, if you look at Desmos from just last year, it only gave me 3 decimal places. It didn't give me those. Now it's giving me 5 decimal places. Lucky for me, my quizzes and stuff say give me 6 decimal places. So you actually have to do at least one Newton's method. I'll say use that Newton's method to find 6 decimal places. But if Desmos gives you 6 decimal places, which it might do someday, because I don't control who, it's a comfort. We get it for free. Beggars can't be choosers. We get what we get. So they gave us 5 decimal places. So I have to change my question to be like 10 decimal places or something. And by the way, even that's getting harder on Desmos because she didn't give me that many decimal places, did it? Yeah, you see, I can't ask for much more than that. 2, 4, 6, 8, 10, 11, 12, 11 decimal places. So I think I could still get 11 decimal places if I multiplied it by 10. I did this. Nope. No, won't do it. So yeah, I don't know. So this is limited. This is, again, if you're doing space travel and you need to have all those decimal places, then definitely. If you're working at a bank and you need to have precise dollars, you don't need 6 decimal places. Okay. All right, let's talk about higher order derivatives. Actually, let's do the questions. The questions today. Okay. I see Suhabi's here. Anyone else? Let's see. I'm going in here. Going down here. I'm asking the same questions as I did last time. I'm only asking them. So, Suhabi, what is calculus?
Calculus is the study of change.
It is. I do have a whole lot of participants here today. Naya and Anusha. Okay. Okay. Nyla. Are you there? I know you're there.
Yeah, I'm here.
Okay, Nyla, what are the other ways of saying IRC and what does an IRC itself, what does that mean?
IRC is instantaneous rate of change. And then other ways of saying it are derivative, velocity, slope of the tangent line, and dy over dx.
Very good. All mean the same thing. Okay, Sarah, I did not see. So Sarah's out. Okay, Jacob, you're there. What's the derivative of x to the n?
N times x to the power of n minus 1.
Right, we've done that already today. And we use the power rule over and over again. That's a good one to know. Tavon, are you here? No. Oh, that's right. Not gonna want to look at it. What is the product? What does the product rule say?
First time the derivative of the second plus second time the derivative of the first.
Oh. Carol's not here to give us the quotient rule. I will stop asking those questions, by the way. You'll notice that some of the questions I'm not asking anymore.
It's just weirdly worded.
What?
So that one's just weird.
The quotient line?
Yeah.
Lots of people. There's all different ways of saying it. The numerator, the bottom, low d high. Honestly, one of my students said, "Oh, I got it. Low d high minus high d low all over low squared." I'm like, "Okay, that does it for you. Whatever." People memorized it. I don't care. My here was here. I saw him.
Here.
Oh, in my mind, that's fine. Okay, I'm here.
X and
What's the derivative of that? What's the derivative of e dx and derivative of natural log of x?
out it. Safety zone.
Just read it.
E over dx.
That's the derivative.
E to the power of x.
E to the x.
E to x equals e to x.
That's it. So the derivative of e dx is e to the x. It is its own derivative. Okay? Nothing. It just means if you take the slope of a tangent line if you have an e to the x, right? When you take the slope of the tangent line, that slope is actually the same as the value. Okay? It just happens to be that way. Don't know why, but that's what it is. Okay, what about natural log of x?
And
The derivative of
the derivative of ln x equals 1 over x.
that's it. Okay, what that means is if you're taking the derivative of the natural log of x, natural log of x looks like, I don't know what that looks like. It looks like this. A capital parabola going up. Take the derivative at a point, whatever that point is, if it's at the natural log, it's the natural log of, so the natural log of 1 is 0. Natural log of 1 is 0. So the natural log of 1 is 0, but if you want to know what the slope of the tangent line is at that point, let me do that one because I'm going to show you. No, it's 1. Yeah, watch. So the derivative, so if I have the natural log of x, that's, do you see it there? I'll make it orange because Halloween, right? There's a Halloween color for it. Okay, you see that? So you see that point right there, 1, 0? What's the slope of the tangent line there? Well, the tangent line would be something like this, right? What's the slope of that line look like to you? Looks like it goes up 1 over 1. Maybe it's 1. And that's what it is. If you go here, the natural log of 5, the tangent line is going to be it's going to be 1/5. See that? See how that looks like it's 1/5? And if you get to like 1, you take the natural log of 1/2, whatever it is, that slope is going to be steeper. Okay? Do you want me to get Desmos to draw them, or do you understand what I'm saying? The derivative of that, so the slope of the tangent line of the natural log is just 1 over whatever the value is. Okay? So the natural log of 1 is 0, but the slope of the tangent line is 1 over 1. The natural log of 2 is that number, but the slope of the tangent line there is just going to be 1/2. Okay? And if you take the natural log of 1/2, that's the value. 1/2. Let's do it this way. Okay, never mind. It's 0.5. That's the value. It's way down wherever that was. But then if you at 1 over 1/2, the slope of that line is going to be steeper. It's going to be 2. Okay, so the slope of the tangent line at 1/2, which is some negative value, that's going to be steeper. So it goes steeper, less steep, shallower. Okay, that's how it changes. Okay. Where's this guy here and why is he there? Okay, we were talking about it. All right, so let's go back to where we were. Where were we here? All right. Nena. Nena's not here? Well, go ahead. Stefan, you can tell me what's the derivative of sine?
Cosine.
Derivative of cosine? You see, you know these things. Where are you looking at them? Anusha, what? I know. Anusha, what does the chain rule say?
The chain rule says that you have to do the derivative of the outside, and then you have to leave the inside alone, and then do multiply like that by the derivative of the inside.
That's perfect. Very good. Melanie, what's the relationship between position, velocity, and acceleration? Position is where you are. Is the first derivative of where you are. What's the second derivative of where you are? Very good. All righty. All right. I also posted some things there. I don't know if you guys know this or not, but I go through all the answers to these questions, or not all of them, but the new ones in here. If you play this video, you can hear it. Mostly do it for the online students. I don't do it for you. But I give you a copy of it if you want it. Okay. And there's also me saying that the higher order derivatives, saying them out like, oh, they're done. So let's take a look at them. Regular derivatives. So this is higher order derivatives. So when you see it written that way, that means the nth derivative. Okay, d to the nth power, dx to the nth power. That just means the nth derivative. If you put a little n in parentheses, that's not the function raised to a power. That means a derivative. Okay. You know what else I didn't include? Sometimes they use Roman numerals. So I put f to the by v, which means the fourth derivative. I forgot all about that. That is used in calc too. All right. This is another notation for the nth derivative. This is another notation for the nth derivative. So all of them just mean the nth derivative of f with respect to x. So what do they look like? So what's the first one? How would you say that? How would you say this? Anyone? Non-derivative square. You're doing two derivatives, so it's the what derivative? Here I wrote the nth. So if it were 2, those are 2's, right? So it's not 2 to the f power, it's second. So that's the second derivative. And what would this one be? There's a second derivative of f. What's this one going to be? Third derivative of g. And what's this one going to be? Fourth derivative of c. And that one right there is the seventh derivative of f. Okay, you can see the answers here. They say second derivative, third derivative, fourth derivative, seventh derivative. Okay. Other regular derivatives. You could take with respect to other different powers like t. It's still the nth derivative of g, but with respect to t. Okay. The nth derivative of y with respect to x. You could also say g double prime if you want. Okay. You could say h triple prime. If you write m, any function raised to the nth in parentheses like that means the nth derivative of m. Okay. All right. So anything in here that's interesting? Oh, I just say number 41. Third derivative of the quantity. And yes.
Respect to each.
Which it's with respect to x. Yeah, it would be with respect to x, because if you don't say with the primes, it usually means with respect to the variable that it is a function of. So this one right here would be derivative with respect to s, not x. Anyway, this guy right here is funny because it's what? When you say that, you're saying what? The seventh derivative. It's in parentheses, the 7 is parentheses, that's the seventh derivative. And here I would say the quantity. So I would say the quantity of the seventh derivative of m, n quantity raised to the third power.
So it has quotation marks. It's
Parentheses means derivatives. If you have a power like this 3, that's not a third derivative. That's cubed. If I had it the other way around, let me just do it this way. This is terrible. This is not a good way to do it. This would be the third derivative of m to the 7th power. But you shouldn't do it. That shouldn't be. When you have a parentheses around a number like that, it means a derivative. You will never see something like this. That's not a third, that's not 3.2 derivatives. As far as I know, it isn't. There's a third derivative. That means taking the derivative 3 times. So maybe we didn't understand what higher order derivatives are. It's just you take the derivative 3 times. When, Melanie, what did you say the acceleration was? And how do we find it? You take the derivative once, and then you do what? You do it again. So if you want the 7th derivative, you're going to take it 7 times. So if you take the derivative of sine 7 times, derivative of sine is cosine, derivative of cosine is minus sine, derivative of minus sine is minus cosine, derivative of minus cosine is sine. So you could figure out what the 7th derivative is because it goes back and forth. But if you take the derivative of x squared, first derivative is 2x, second derivative is 2, the third derivative is 0, fourth derivative is 0, 0, 0, 0, 0. So sometimes 7th derivatives just go away. You'll learn that in Calc 3 if you use it. Okay, what else? Evaluated derivatives. You can evaluate it. You can put a number in there. That's the nth derivative of evaluated at a. Nothing new. That notation is not particularly new. You put a number in there, it's evaluated at a. Okay, so this is the same notation we might have seen before with evaluated. So you see, this is, how do we say this first one? Suhave, how would you say number 65 if you had to say it?
The derivative, wait,
Which derivative? Which derivative?
the fourth,
Fourth derivative, yes.
the fourth derivative to respect of
F of x. You don't have to say what's f of x.
with respect to, sorry, what was that?
You don't have to say with respect to x.
Okay.
You can, you don't have to. Fourth derivative of f of x. And what? What does step 3 say?
With respect to 3.
No.
I'm not sure.
So it's the fourth derivative. Here, let me just give you the answers here. It's the fourth derivative of f with respect to x evaluated at x equals 3. Okay? Well, you could just say the derivative, fourth derivative of f of x evaluated at 3. Or you could say evaluated at x equals 3. Okay, but it's evaluated at 3. When you put a number in there, you're evaluating the fourth derivative. Okay, how about this next one? Anyone? What's that say?
7th derivative of evaluated.
Yep, there you go. 4. That's it. What? That parentheses means it's evaluated. And you don't do it this way. You find the 7th derivative and then you plug 11 in. When you're taking the derivative of a function, what I'm saying to you is this. Let me show you this. When you say that's a function, right? When you put a number in there, okay, let me just write it this way. What's the derivative of the sine of pi? Well, let me say pi over 6. There. It's 0 because you know why? Because it took the sine of, what is the sine of pi over 6? That's just a number, right? 0.5. What's the derivative of 0.5? 0. If you want, so you don't want to even write it this way, but if you want to write, hold on. f of x equals that. And then if you want, watch this now, if you want f of pi over 6, you get a different answer. Because one is the function, we're writing the derivative, and then we're evaluating it pi over 6. If you write it this way, you just have to be very careful, because the way it reads that is I evaluate the sine of pi over 6, and then I take the derivative of it, and I get 0. As opposed to taking the derivative first and then evaluating it at pi over 6. Okay. But I'm telling you, with our notation, when we write a number in there, we don't mean plug the 11 in first. So if we plug the 11 in first, we're just going to get a number, and then the derivative will be 0, whatever derivative, 7th derivative. When they write it this way, they really mean take the 7th derivative first and then plug the number in. Okay? They mean create a function, a new function, g of x equals the 7th derivative of x. Okay? And then evaluate it. And then plug in the 11. And then do g of 11. That's what that means. So when you write it that way, it doesn't mean plug the number in first. It means do the derivative first and then plug in the number. Okay? All right. There's also hyperbolic things here. Hyperbolic trig functions are there. We already went over those. How do you say them? How do you say it? Oh, here's one. Example 2. So example 1 is this hyperbolic sine squared of the quantity 2x and quantity 4. But this one right here, you have to be careful. This is hyperbolic cosine of the quantity x squared and quantity plus hyperbolic cosecant of x. Okay, you have to make sure that you say quantity and quantity with x squared, because if you don't, it's going to think you mean this. It's going to think you mean to ramble it on like that. If I want to read that, that would be the hyperbolic cosine of the quantity x squared plus hyperbolic cosecant of x and quantity. Do you see the difference? And would you put a -1 power? What does that mean? Remember what -1 powers mean? Anyone? No. What does it mean when I write sine? What happens if I wrote sine to the -1 power? Let me just type sine. What does sine raised to the -1 power mean? It does not mean 1 over x. It doesn't mean 1 over, it doesn't mean sine 1 over the sine of x. What does it mean? Do you remember this from pre-calculus? You had me for pre-calculus too, didn't you? What did it mean when we put a function and we wrote, what does this mean? What does that mean? Do you don't remember? See how quickly it goes. Anyone? Neither. Do you remember what the -1 power means? It doesn't. 1 over
Is it the inverse?
It does. It means inverse. It's the function. It's an undoing function. It doesn't mean 1 over. It's the whole reason we have the secants and the cosecants, so that we don't confuse them. Do you understand? Secant of x is 1 over cosine x, which is another way of saying cosine x raised to the -1. Okay. Okay, that's all true. But what is not true is this. It's not equal to, it's not cosine raised to the -1. That's, I don't want capital. That's not the same. Putting that -1 on the outside is not the same as putting it here. If it was a squared, it would be. If I put a 2 there, put a 3 there, that means this, third power. That's fine. Those do mean the same thing. But when it's -1, that's very specific notation. Remember, what is math? Math is a what? Math is a language. And so in this language, when we raise something to the -1 power, normally it means 1 over, means the reciprocal. But if it's a trig function or any function that you raise to the -1 power, it means inverse. Okay. All right. So I just want you, that's actually an interesting thing to know. If you have this, that means the function raised to the first power. Okay. If you have this, it means the function squared. Okay. If you have this, does that mean? That does not mean the function squared. It means what? It's the second derivative. Okay. And then what does this mean? That's the inverse. So yes. So we've run out of ways of writing things. So we have fancy notations to confuse people. That's why so many people love math. Okay. So for you, for homework 4, there isn't much in the way of higher order derivatives, but they're easy. So here's question 10. Compute the following. What am I asking you for there? I went through that big deal of telling you that it has to be in parentheses and it's not in parentheses. Okay. Now, what am I asking you for there? Okay, so how do I find it? How do I find it? Right. So what's the derivative of that? 3x raised to the third plus 14x. That's the first derivative. So that's g prime. Okay.
Okay, so the power just disappeared.
Derivative, it's a constant. Jake, what's derivative of constant? 2. All right, I'll Jake out the power a little second. Melanie, what's the second derivative going to be? Just take the derivative of line 122. Three times 20 is x raised to the drop the power. So what's that going to be? Take squared. Okay. What's the derivative of 14x? Devon can help you with that. What's the derivative of 14x? 14. 14. The x is fine. Anusha, can you give me the third derivative?
I'm not completely sure. Would it be 120?
And x raised to what power?
To no power?
To no power, first power.
Yeah, to the first power.
That's correct. And what's the derivative of 14? That's a constant, so that's 0.
Yeah, 0.
Okay. Who wants to do the last one? Nyla, you want to do G to the fourth? Which the fourth derivative?
G to the fourth is just 120.
Yep. And what is every derivative after that? Fifth, sixth, seventh, what are all of them going to be?
0.
0. Thank you, Jake. They're all going to be 0 after that. Okay. All right. Easy enough? Finding higher order derivative is not that hard? All right, then let's break up into our groups. Although we seem to be missing some people. We have 2 groups in this class, right? Melanie, your group, you and Jake are in that one group. And Devon, are you in you're in that group too? Nyla, Anusha, what group are you guys in?
I'm in Javon's group.
I'm in the other group.
Anusha and Suhave are in the business group,
Yeah, we are.
but Nyla, you're in with them. So one of you gonna log on so Nyla can be in your group with you? Oh, which group are you in?
I was in the
Business?
business group.
So you're in, so can you log on because you have 2 people online? Okay, very good. But you're leaving. Did you give them your link? The link is there?
Double check. I'm pretty sure it is.
I just want to make sure because otherwise they're going to be sitting there twiddling their thumbs. Uh-oh. So you can join whichever group you want. So let's see. Anusha and Suhavi are in group 1 and Nyla is in 2.
It's on my computer.
Mahir, you're going into 1, right? Here. Yes. And so Jake or Melanie, can you log on to Zoom from your computer so that you can talk to Nyla? Okay, so if you finished transcendentals, you should move on to, oh, these people are in the breakout rooms, right? Are they in the room with you, Mahir? No, they're not. They're not yet because I still see them. Anusha, you can hear me still?
Yep, I'm still here.
Okay, so this is what you're doing. If you're done with the transcendentals,
Posting it on.
right?
We're posting it.
We're gonna do mean value theorem, but you've left them the thing they can do for you. Or if you've left them the thing. Okay, mean value theorem is the next one. So for mean value theorem, all you have to do is turn on this line. That's the average rate of change. Okay, to see this, the average rate of change is 50. And you see, all you're going to get is a horizontal line. Okay, that's the average rate of change between the A and the B values, whatever they're set to be. So make sure you know what they are. You might want to bring them down here. That would be nice. Bring A and B down. So the mean value theorem between 0 and 20, the average rate of change is 50. Does everyone understand that? We've already done average rate of change. We only did it that one time, but that's it. Average rate of change between 0 and 20 is 50. 50 miles per hour. That's the average rate of change. Got it? Good. And the next thing we're going to do is we're going to graph y equals the derivative of that same quartic regression. So I graph the derivative. Now, the derivative of a quartic is going to be a cubic, and it looks like that. So that's the green line. And all you have to do is click on the intersections and find them. 7.53. And there's another one over here, 17.48. And there's another one here. Boom. So if you can click on those 3, the producer is done. That's all the producer has to do is show those intersections wherever they might be. There's at least one. Actually, the producer should really do this. I'm sorry, the producer should do more. The producer should click on that. Ooh, that's terrible. Why is it terrible? 7.53. It's terrible. Oh, what's going on here? Oh, I know. So the producer should do this. The producer should actually turn them off. Once you have the answers. So once you have those answers, put them down either in the function, like 7.53 and 17.48, put them down in here, or put them in a table somewhere. But I don't need this anymore. What I wanted to do, this would be the best thing to do. Go back to your data and turn on the original Bordick regression. Let me just reduce that. This is a beautiful picture of what the mean value theorem says. It says, you see that right there? That's the tangent line. Do you see the orange line? That's the average rate of change between 0 and 20. Right about here, they're parallel to each other. So what I'm saying is the average rate of change between 0 and 20 was 50. And that happened right here at 7.53. It also happens again at 17.486. Okay, do you see how close they're parallel? Again, they're parallel here and they're parallel there. But I use this slider so you can see they're not parallel. That orange and purple tangent line are not parallel. They're parallel here. They're parallel around there. They're also parallel much further down here. The negative numbers, they're parallel, but that one we don't care about because it has to be numbers between 0 and 20. But whatever your A and B are, we can only care about those answers. So that's why we only care about 7 and 17, and we don't care about minus 1.266. Okay, don't care about it. All right, if you can get that, that would be great. Okay, producers try to do that, and then we still have that's a little ahead. So if you did finish up last week's, finish up that first. Okay, now you can go to your breakout rooms. Okay, I got Anusha, Mahir, and Suhave in room 1. Naila and Melanie in room 2. We're missing Sarah is in your group. We're missing Kara is in this group. And Devon just left. So that's 3 people. That's everybody. We only have 9 people in this class, so small. But here, are you talking to him or them? Are they talking to you? You're in it? You're not in it? It says you're in it. Oh, wait, hold on. How about now? I don't know what's going on with the screen.
I think she did the, what's it called, graphing.
Yeah, she produced it, but she's a
Oh, are you talking to her at all? Can you hear her? Is she there? You're awfully quiet. I feel like nothing's going on.
You know the same about I
You
tried.
have an earbud in. Oh, well, you didn't hear her. Oh, see. Yeah. Hey, do you want to move up to 7? Oh, sure. If he. Okay. Can you hear me, Nyla? Anusha?
Yeah, I can
No.
hear you.
Okay, good. Melanie's gonna leave so that because she's here. Okay, so let me just finish up what we're doing. First of all, I want to say that we are, if you look under announcements in this class, right? Way down at the bottom, there is the link to my live stream. And there it is. So if you have to watch the live stream, you can, but please, you won't count as attendance. I'm perfectly happy that you were home on Zoom. That works for me. And so next time is Mod 5. And Mod 5 is when we start, at the end of next week, you'll have the test. So it will actually, the derivative test is in Mod 5. Okay? And that's where you will see it. It's not there now, but I'll probably have it put up over the weekend and probably won't show up until next Friday. Okay. I'm not sure if Mod 5 is even on the derivative test. I don't think it is. Okay. Any questions? Are we good? Okay. All right. Then I am done for the time. And I am shutting down the live stream.